Hey there, all my wonderful students. Dr. Mandis here, and today I'm going to talk to you about ice tables. Not ice as in like ice on a hot summer day, ice or a cold winter day, ice, but ice is in initial change equilibrium tables. Here's a gig. Okay, equilibrium solve. I'm assuming my students can do plug and chug into an equation. Like if you have an equilibrium expression that looks like that, I'm assuming that given one unknown, other numbers to plug in there, you can do whatever algebra you need to solve it. All right. The problem is that what if you're not given equilibrium values? This equilibrium expression goes with an equilibrium equation, okay? If they're not equilibrium values, you can't use them. Sometimes you're given initial values. You're going to play around some stoichiometry, do something like that, get to some equilibrium values. Then you can plug them into the groovy little equilibrium expression and solve for whatever you need to solve for, okay? But here's the gig. Doing all the stoichiometry can kind of get buried down a little bit at times. These tables exist so that you can sort of organize your thoughts. They're initial change equilibrium tables, otherwise known as ICE. Okay? Friendly kind of ice. All right? But here's the gig. All you're going to do is you set up your reaction, like here is your reaction. Beneath that, I usually line up this little line right here to sort of just keep my mind straight one way or the other. You know, to the left are reactants, to the right are products. On the initial first line that we have going on there, all right, let me just make that line better. You got reactants up here, okay? I mean, the initial conditions up top. And then you're going to have what we call a change. Things would change. I pop these into the pot. They react however they're going to react and settle into equilibrium. And these would be the equilibrium values. All right. You have to understand that the table is set up so that it adds up. Whoopsie daisy. Didn't mean that. It adds up right across here. This is an addition line. Stink. The initial plus the change get you to equilibrium. Given the fact that it's really one problem, but it's really a bunch of problems. And here is one problem. Given 2 out of 3 of those conditions, you should be able to come up with a third one. All right. Given 2 out of 3 of those conditions, you should be able to come up with the others. That means if it's initial plus change equals equilibrium, given 2 out of 3, do the algebra, figure out what's going on. Right now, today, we're going to try to figure out equilibrium. How do you get to the equilibrium values? Well, you plug in your initial values. Right now, I just wrote concentrations of whatever with a little circle, the knot down there tell you the originals, alrighty? Then you have to figure out which way will it shift. Is it going to make more of it or use it up? In this case, we just assume we're going to shift to the right. We're going to pretend Q is less than K, we're shifting to the right. I'll give you better examples later that show you exactly what you're going to do. But you can calculate a Q. Q tells which way it's going to shift. If we're shifting to the right, that means we're going to make these, that's why they're pluses, and we're going to use up the reactants, which is why they're negatives. Where do the coefficients come from? The equation. 2a is 2x, 2c, 2x, 3d, 3x. If it's a 1, keep it a 1. Do you have to write the 1? Gosh, no. I wrote the 1 for you. Okay, so that's where the coefficients come from. It's really easy. The number in front of x is the coefficient from the equation. Don't overthink it. And then add them up to get to the final line. Once you have the final line, you can plug them back into the k, which we have down here. If you look at that, then you have a bunch of unknown values there, but things would work itself out. Alrighty, let me give you a different example where it shifts, where you don't have to use Q, okay? Down here, let's look at this example right here, okay? How do you know which way it's going to shift? You have to use Q, but really you don't, okay? 9 times out of 10, something's a 0. Like here in this example where the initial concentration of A is 2 molar, they're saying you start with A is 2 molar. Well, if you had C and D, they would tell you. I would tell you. So you can assume that C and D are 0. So you set up your equilibrium equation, your equilibrium expression right next door, so you can plug into it. I didn't write the general one. Just getting lazy. Sorry about that. All right, and the initial concentration line, A is 2, C and D are both 0. Now, which way will it shift? Okay, remember, equilibrium is about going forward and going backwards. We can go forward because we have some amount of A. We can't go backwards because we don't have either one of these puppies. Can't react things that you don't have, okay? So the reverse reaction is not going to happen. So the only way it's going to go is to the right. Well, if you run to the right, you make C. Since it's a 2, it's plus 2x. You make D. Since it's a 4, it's plus 4x. Back here for A, we're going to use that up and that's minus 3x. That goes back to Le Chatelier's principle, where you say you'd have a shift, you make the stuff that you're making, they go up, on the backside they go down. Well, these are pluses, those are minuses, just harkening back to Le Chatelier, or Le Chatelier, however you want to say it. All right. But when you get to something that looks like this, it's kind of intimidating. You got some squared terms in there, some cubic equation. All right. It might be difficult to hanker through that math unless you're just going to punch into a computer and let the computer do it for you. But happily, there's a shortcut. Okay. If you understand sig figs, I put it down here. I don't know why I tucked it in there. But 2.0 minus 0.01 is not 19, isn't 1.99. It's 2.0 because by sig figs, it's the least number of decimal places. You can only have one decimal place. So using this whole idea that we have error to our measurements and such, that limits you. There's a thing called a 5% rule. And basically, x is going to be small. And so every time you have, something minus x, you can pretty much just say it's that something because it's just a little value. It's like, say you're like one of these millionaires. You got $1 million. You spend $100. You got $1 million, man. Seriously, it's not that much. Okay. If you have $10,000 in the bank and you spend $1, pretty much got $10,000 in the bank. If you have $1 and you spend 50 cents, that's an issue. Okay. So you got to make sure that everything is straight. Okay. Anyway, so there's a 5% rule. So given this example, we'll apply that 5% rule. Given the system, given this example equation right here, we have A going to C and D. There's a K value. There's our initial amounts. So what you want to do is run through this first, second, third thing if you're reading it while I'm talking, okay? Set up your ICE table, which is right here, okay? Point to A, 0 and 0, C and D. That means you got to go to the right because you can't go left, so you have that, okay? Add them up and you get the equilibrium line. That goes into your equilibrium expression. It's nice if you just set up on a column to the right because then you can sort of see things all the time and it just is clearer and nicer. If you plug, again, I didn't write the general expression. Interesting. Anyway, plug it in and you get this groovy little equation here, which looks kind of ugly and kind of complicated, but k is small, so x is going to be small. So 0.2 minus x is going to be 0.2. And that simplifies to something a lot nicer. Okay? That simplifies to this little cubic that we can solve by taking a cube root, and we get x is 0.037. Getting back to that 5% rule, initially we had 0.2a. Well, if you only lose 0.037, that's a 1.9% drop. So that the assumption's valid, so we're good to go. So we take this value of x and plug it back into our equilibrium line. Okay? You have the concentration of A, C, and D at equilibrium. The equilibrium line tells you what they're equal to. All I did was recopy it down over here into A, C, and D, plug in the value of x, and you get your wonderful concentrations at equilibrium. Later on, when you study acids and bases and other things, you will use those concentrations at equilibrium to do further studies. Right now, that's the end goal of these problems. Hope you understand it, learn it, and like it. Have a great day. I'll talk to you later.